Hi students, welcome to Structural Engineering Lectures and welcome to the new playlist on analysis and designs of the structures using STAAD.Pro, ETABS and Excel spreadsheets. In today's class, we shall see the design of a ground plus 3 floor or story RCC framed building by STAAD.Pro. It's a tutorial. We'll try to see the designs of the slab, beam, column, footing, staircases using Excel spreadsheets, as well as we'll see the executable drawings using AutoCAD. All these designs will be conforming to a limit state method of IS 456-2000. This is how the building what we are going to see, students, right? Whereas in the previous class we have seen the design of a single story RCC building by STAAD.Pro. I hope you enjoyed the discussions there. Therefore, if you have enjoyed the discussions, don't forget to click like, comment, subscribe and share to our YouTube channel. Right? Before we see the actual discussion, student, let us move to the brief profile of mine. That is about the speaker. Right? I, Dr. D. Rupesh Kumar, obtained my BTech Civil Engineering from Nagarjuna University in 1994, MTech Structural Engineering from JNTU Hyderabad 2000, and PhD in Structural Engineering from JNTU Hyderabad 2009. Presently, I am working as Associate Professor in Department of Civil Engineering, University College of Engineering, Osmania University, Hyderabad, Telangana State. I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate and postgraduate levels. My research areas include reinforced cement concrete designs, steel designs, structural analysis, finite element analysis, earthquake engineering, bridge engineering, structural optimization. I have published 45 research papers at international, national as well as international journals, conferences, organized 3 international conferences, 11 national conferences and workshops, attended 43 workshops, visited 2 countries, delivered 13 guest lectures and edited 2 books. At present, I am supervising 14 PhD scholars and supervised 30 ME scholars. I am actively involved in the various consultancy works that are offered by the department and completed over 750 design proof checks as of now, and 150 plus designs of RCC, steel, composite, low-rise, high-rise, multi-stored buildings, and that of the rail and road bridges. Right? Once we see this brief profile, student, let us say what we are going to do in today's class is this design, the design of a G+3 floor RCC 3D framed building, right? RCC 3D framed building, right? And so far, we have seen 2 components of the design, student, right? One is the design of the slab. The second one is that of the design of the staircase. Now I'll go to that of the STAAD modeling now. Right? Now before I go to the STAAD modeling, student, what I'll do is I'll show the different loads. The different loads are even. Let me quickly go to that of the third component, design as that of the design of these plinth beams. Design of that of the plinth beams, right? For whose dimensions are assumed as 230 by 300 mm, right? However, these external plinth beams, EPP, which are supported on the CRS masonry, and the internal plinth beams are supported on well compacted soil, over which the PCC bed of 150 mm thick PCC bed is provided, over which the cross section is provided, or the longitudinal section of the beam is resting over that PCC bed like this. That PCC bed, right? That is how it is looking like this. Right? That is how it is looking like this, right? That is how. Now let us examine this design. However, as per this SP24, now these beams are designated as the graded beams. Therefore, now I'll initiate that of the designs of these graded beams and slabs. Therefore, now I'm there in that design of the plinth beam, student, right? There is no load from the slabs, right? Whereas the live load on the beams is is calculated as 6.5, right? 6.5, right? Or before I go to this design, let me I'll come to this, right? 6.5. I'll explain how I got this 6.5. Just bear for a moment, right? I'll come to this, right? This is the weight of the brickwork, right? That of the 150 mm thick. This 0.15 multiplied by 3 minus 0.45. That works out 6.5 kilonewton per meter, right? 0.15 multiplied by 3 minus 0.45 height multiplied by 19.2 kilonewton per meter cube. That of the density of the brickwork, right? That works out 6.5. I'll also show at a later point, right? And the sulfate of the beam. Now the plinth beam dimensions are assumed as 230 by 300. Therefore, that multiplied by density of concrete 25 kilonewton per meter cube. It works out say 1.73 kilonewton per meter. Therefore, the total load, unfactored load, is equal to 8.23. However, if I go to this AutoCAD drawing, at maximum I do have a maximum span of 4.2 meters, right? Or even now we can see that I don't have a span more than this 4.2 meter. Therefore, now I'll give that input for the external plinth beam, student, right? External plinth beams 4.2 meters, right? Whereas for that of the internal plinth beams, you please see that this beam is just supported, right? This beam is just supported on this column as well as that of this column. Therefore, here the slab span is more. Therefore, the slab span is more. Now, here the center of this column is 5.57. Therefore, out of this two plinth beams, right, this external plinth beam or that of this internal plinth beam, this internal plinth beam, though this is supported in the perpendicular direction also, right? Also, now I'll design assuming this as the main support and this as the secondary beam. Obviously, because it is supported over the main beam here, right? Therefore, the secondary beams, right? Hence, that is the design I'll initiate. Right? Therefore, 5.57 meter. Once I give that input, right? 5.57 minus that of this. If I just exactly measure, right? Therefore, that 5.57 is from the center of the plinth beam up to the end to the top of the center of the plinth beam. Therefore, now I'll measure what is that clear distance between these. It now works out say a value 5340. That input I'll give, right? 5340. Therefore, that input I'm giving here, and I'm proceeding with that, right? 5340 minus that of okay, or even you can say 5340, right? 5340. I'm just changing because I just measured from the AutoCAD, right? And the grade of the concrete M25 and FI 500 grade steel, right? Therefore, I'm assuming the main steel as a 12 mm dia and cover to the beam as a 25 mm. Therefore, the effective span is that 5.34 plus width of this beam 0.23. Now it works out 5.57 meter, whereas that factored load 1.5 multiplied by that total load by 2, it works out say 34.36 kilonewton, as well as the factored bending moment, right? That actually code says SP24 says that as per this SP34 we are designing this as a graded beam, student, right? From class 6.9.5, page number 78. We do have only the code says that just if you provide just 3 1010 mm dia bars, it is sufficient. But nevertheless, I am designing this for a bending moment of WL square by 24, because my if I assume the beam to be fixed at both the ends, it is WL square by 12 is that bending moment, but I am assuming 50% of that. Therefore, even SP34 has not given any such coefficient, right? Whereas in the other literature, you would have this coefficient, right, by 24 or even 30 also in other Indian standards, right? Therefore, I am taking that by 24. If I take that 24 divided by 24, I'll get a bending moment of 15.95. Therefore, now from this IS 456 class G 1.1.B, page number 96, now I'll calculate what's the depth required. However, the depth required is much less than the depth provided. Therefore, the section is under reinforced. Therefore, what is the area of the steel required? Now, even the MU limb I'll calculate, whereas that MU limb is much MU is much less than MU limb. Therefore, the section is to be designed as a single reinforced section only. Therefore, AC is equal to 0 in such a case. Therefore, using that formula what you have seen just now from IS 456, I'll calculate using this formula. MU is equal to 0.87 FIAST D multiplied by 1 minus FIAST divided by FCK BD. Then solving this, now I'll get what is that AST. Therefore, that AST now works out a value of 213 mm square. Therefore, we already assumed 12 mm dia. Therefore, each 12 mm dia can provide 113. Therefore, 113 multiplied by 226. Even if you provide 2 12 mm dia bars for even this 5.34 span, which is already supported on the PCC bed resting on the hard soil, like this, right? This is the hard soil, student. I'm just showing that the plinth beam is resting on this hard soil, right? Therefore, that's why the movements are even reduced by 50%, right? Therefore, there I'm getting just two 12 mm dia bar at the top as well as 2 12 mm dia bars at the bottom. Just 2 12 mm dia bars at the bottom. Just 2. Therefore, once I get this, then what I'll do is now let me check for the shear reinforcement also. I'm assuming 8 mm dia 2-legged stirrups. Therefore, now nominal shear stress will work out 0.56 Newton from mm square, whereas the percentage steel provided works out 0.34. Therefore, from this IS 456 table 19, now I'll interpolate for 0.25 and 0.5. The values are available in page number 73 of IS 456. Just wait for a moment, right? 73. I'm just going to that 73, right? Therefore, if I interpolate, now what I'll get? Therefore, there is the value is 0.36 for 0.5 percentage of steel. It is 0.49 for M25 grade concrete. Upon interpolation, I'll get this result. Therefore, 0.42. However, from the same code, from next table, the maximum shear stress for M25 grade concrete is equal to 3.1 Newton per mm square. Therefore, my nominal shear stress is much less than the permissible shear stress, student, 3.1. Therefore, the grade of the concrete need not be upgraded. However, you please see that tau V is greater than tau C. Hence, I need to propose the shear reinforcement as per this same page number 72 IS 456, right? To resist the shear by the stirrups is equal to VUS is equal to VU minus tau C BD. Therefore, now it works out 8.49 kilonewton. The stirrups need to resist 8.49 kilonewton meter, right? Just wait for a minute, right? This is all right. These stirrups need to resist 8.49. These stirrups we are designing. Just now we have designed these main steel, too tall at the top, too tall at the bottom for the plinth beam. Not here actually here for the plinth beam. Now I'm just showing that of the roof beam, right? Therefore, now I'm designing these stirrups. Therefore, those stirrups, if I design now, I'll get the spacing required is equal to how much. Therefore, I'm getting that spacing is equal to 202. However, the spacing as per that same code should not be more than 3D. Therefore, 3 multiplied by the effective depth. However, this 202 is much less than that 3D are for vertical stirrups. Vertical stirrups are 300 mm. In the worst case, it should be not more than 300 mm, like this, right? Let us revisit that, right? Therefore, even let me check that, right? Therefore, in the worst case, the code says that, right, like this. From this just now we have seen, right? Sorry, the spacing should not be more than 0.75 d, student. I'm sorry, right? Right, from this code specification from class 40.4, page number 73, the minimum spacing is 0.75 d or 300 mm. However, here I do have a effective depth 300 minus 25 minus 6, right? I do have 269 multiplied by 0.75. I'm getting 202 or 300 mm, whichever is minimum, whichever, right? Therefore, that is how 202. However, even the code says that the minimum shear reinforcement should be provided. Minimum shear reinforcement should be provided. Therefore, ASV by BSV should be given by this formula, should be greater than or equal to 0.4 divided by 0.87 Fi. Therefore, that now works out for 8 mm dia strip, student. It will work out 394. However, that minimum stirrups will not govern the design. However, the design stirrup will govern the design, which is now worked out as 202 mm. Therefore, now I'll provide that stirrup, right? Hence, provide 8 mm dia 2-legged vertical stirrups at 202, or say 200 mm center to center. That is what my design of the plinth beams, right? That is what I am doing, right? You can see just now I have designed this, right? 230 by 300 mm, student, right? Which is, right? Actually, I just got only 2 12 mm dia at the top and 2 12 mm dia at the bottom, but nevertheless I am providing one more extra rod, right? Now so I am providing 8 mm dia, these stirrups, right? 8 mm dia 2-legged vertical stirrups, 8 mm dia 2-legged vertical stirrups. It is spacing of 200 mm center to center, right? Similarly, however, for the external beams, either you may provide the same 3 numbers. However, here the span is less. Therefore, even if I design, right, using that, now with the lesser span, I'll get only just 2 12 mm dia bars, right? That is how what I am designing, right? Therefore, that design I'll do now. Hence, I'm going to that. Let me show that quickly, student, right? However, that main span, right? That of the main span is 4.2 minus 230, right? 4200 minus 230, student, right? 230. Therefore, I have to have 3970. Therefore, if I give that as an input, 3970, what I'll get is say same 3.97, right? What I'm getting is still less, actually 146 mm square only. Therefore, 146 mm square divided by 113. Therefore, for 2 12 mm dia bars, even 8 mm dia 2-legged vertical stirrups, 8 mm dia 2-legged vertical stirrups. It is spacing of 200 mm center to center. 200 mm center to center as appropriate. Therefore, those designs I am showing here in the drawing, right? Therefore, that is how my design. Now is 2 12 mm dia at the top, 2 12 mm dia at the bottom, and 8 mm dia 2-legged vertical stirrups, 2-legged vertical stirrups as the shear reinforcement, right? Now, hence I have just concluded that of the third design, student, and let me show the designs in the form of an executable drawing. Therefore, just I am having each of the time an executable drawing. Therefore, I am showing that these are the external plinth beams, internal plinth beams, and what are their cross sections, as well as that of the reinforcement details, main shield, that of the top shield, as well as the bottom shield. I am providing these steel through and through. I'm providing these rods through and through like this, right? And that of the stirrups, right? These details I have shown. Therefore, these are the design of the third component, student. This is the design of the third component, right? Once I do that, then what I'll do is I'll move to that of the other design, student. I hope you are understanding these discussions, right? Then I'll move to that of the STAAD design. But before I move to that of the STAAD design, student, what I need to do is I need to calculate the loads. Therefore, now I'll move to that Excel sheet where I want to calculate all these loads. right? I hope you're understanding these discussions. Therefore I'm just calculating these loads, right? What are these loads? Therefore just now we have seen the thickness of the slab as 100 mm, right? And the self-weight of the slab 2.5 kilonewton per meter square, and the floor finish is 1.25, and partitions even we have taken as 3 kilonewton per meter square. Therefore now even if I exclude that 3 kilonewton per meter square, right, just dead load plus floor finish itself is working out 3.75. This will my input in STAAD, 3.75 kilonewton per meter square, and the imposed load in all the rooms is 2 kilonewton per meter square, whereas in the corridor as well as that of the staircase it will be 3 kilonewton per meter square from IS 875 part 2, and that of the imposed load on the terrace floor, where access is already provided. Therefore I can use 1.5 kilonewton per meter square from IS 875 part 2. Therefore these are my inputs, student, right? Then I'll calculate that of the balcony loads, right, on this cantilever portion 1.2 meter, right? There I'm getting the dead load from the balcony 1.2 multiplied by 3.75, 4.5 kilonewton per meter, as well as the live load from the balcony as 1.2 multiplied by 2, because 2 is the live load, right? 2.4 kilonewton per meter, and as well as the live load on the terrace slab as 1.8 kilonewton per meter. Then just now we have seen the design of the staircase. There we have seen 150 mm thick, right? Therefore all these loads, riser 150 mm and tread 300 mm, and the inclined length factor is equal to 1.12, and span also we have seen 4.1. For that, what is the self weight of the waste slab? It works out 4.54, and self weight of the each step of 0.15 by 0.3, that of the RCC step 1.88, and floor finishes 1.25. Now I'll get the total summation of this is equal to 7.67. Therefore the UDL due to the dead load is equal to that span 4.7 multiplied by this UDL 4.67 multiplied by this inclined length factor 1.12 divided by 2, because that half will go to the bottom of the beam, the right half will go to the top of the beam, right? Therefore that is our 17.6, because half the load will come to this beam and half the load will go to the top beam, right? 17.6, or half the span, either of the two is true, right? Because 4.1 by 2 is the half of the span, right? Similarly, the imposed loads will be 4 kilonewton per meter square, and UDL now even I am assuming that even if overcrowding is happening 5 kilonewton per meter square. Therefore with that 5 kilonewton per meter square I am actually assuming overcrowding now. Actually for these just 8 flats, 8 multiplied by 4, 32 flats, overcrowding will not be possible, because in total over 32 flats, even if in each of the flat one couple along with 2 children, 4, 32 multiplied by 4. Therefore at maximum 128 people will be using, or at maximum not more than 150 people will be using. Therefore it will not be liable for overcrowding. But nevertheless, assuming overcrowding, therefore now I am having the UDL due to imposed loads or live loads on these is equal to, I'll get 11.48 or say 11.5 kilonewton per meter. This is for the analysis of the staircase, student, right? Now I'll calculate what are the wall loads. Just now I told during the plinth beam that I am taking a wall load of 6.5. How I am getting that I am explaining, right? Therefore that is how the self weight of this 0.15 thick brick wall. This thickness is equal to 0.15, right? 6 inch wall. Therefore 0.15 multiplied by 3 minus 0.415 multiplied by 19.2, from the dead load intensity of the brickwork is equal to 19.2, and there are the openings in between also. Therefore I'll assume that 15% of them are openings. Therefore now with that now I have the load calculated as 6.5, student, 6.5. Therefore now it works out the dead load of this 0.15 walls as 6.5 6.5, and that of the parapet wall, right? As say the parapet wall height is equal to 1 meter and its thickness is just 4 inch, right? 4 inch. Or let me go back to this drawing, student, right? This is the parapet. The parapet will be just considered as 4 inch thick, right? Therefore, for that now I'm calculating what is that load, right? Now that load works out. Load now works out a value. 1 meter multiplied by 0.1. It works out 1.92. Therefore, I'm assuming it as 1.95. 1.95. Therefore, once I get this, student, what now I'll do is, I'll simply proceed to the top the STAAD designs. Right? This is my the 3D model of the STAAD. Therefore, you can see that this is ground floor plus 3 more floors. Therefore, this is my STAAD model. Even now you can see that I do have staircase headroom also, right? Therefore, that is how my staircase headroom is also shown. I'm seeing that entire 3D model, right? The slabs are not modeled here, right? This is a bare frame. What I'm showing is that of the bare frame. Now either you can see from the bottom, right? That's the beauty of the software, or an eye-bird's view, or the elevation from front, right? Or an eye-bird's view from top, as appropriate. Any view you can see, student, right? This 3D frame we are analyzing, right? Now, before I analyze, let me also see what are the other loads, right? Wind load and as well as that of the earthquake loads. Now let me go to that of the wind load and earthquake load, student, right? I'm there in the next page. That of the wind load and earthquake. The wind loads will be calculated as per this IS 875 part 3 2015. The new code, student, please. I'm referring to the new code, right? If you are further interested, you may just visit our design of steel structures. There we have elaborately discussed this new code IS 875 part 3 2015 in one video. Please revisit it. Similarly, you may revisit another video in that same playlist, IS 1893 part 1 2016 latest earthquake code. 2 videos we have dedicatedly discussed there, all the code specifications pertaining to each of these. Please revisit it if you wish, right? Then now I'll calculate the wind loads using this IS 875 part 3 2015 code, student, right? Therefore, from this let me just go back to this IS 875 part 3, IS 875 part 3, right? These are my part 3, student, right? Wherein the code says that design wind speed Vz is given by VV multiplied by K1, K2, K3, K4, where Vz is equal to design wind speed at a height of Z in meter per second, and Km is a probability factor or risk coefficient, and also K2 is the terrain and the terrain roughness and height factor, and K3 is the topography factor, and K4 is the importance factor for the cyclone regions, right? Whereas the code says that the risk coefficient K1 shall be based upon for normal buildings for a return period of 50 years of the mean return period. Therefore, such values are available in table 1, right? Similarly, that of the K2, terrain height factor K2, right? Then what is that terrain? Now I am assuming that my terrain is category 1, where I am having exposed open terrain with few or no obstructions. Hardly their obstructions are varying from 0 to 1.5 meter. That is my assumption. You may differ also, right? Like that, other category 2, 1.5 to 10 meter, category 3, they are there, but I am assuming category 2, right? Therefore, from this table 1, right? From this table 1 for normal general building, or my Hyderabad is there in right? My Hyderabad is there in a basic wind speed zone of 44 meter per second, right? Therefore, because the building is a generalized building, therefore, what is K1? What is K1 is 1. I'm just making note of that, right? Therefore, that is how I've just noted down from this IS 875 part 3, the new course student. Then similarly, let me go to that of the other calculations at a quicker pace, right? These are just now shown from figure 1. From figure 1 of page 6. Let me go to that figure 1 of page 6 also, right? There the basic wind speed is given, figure 1. Let me go to that figure 1, right? Just wait for a moment, right? This is my page 6, figure 1. There I do have the basic wind speed, of this entire India, right? And then now Hyderabad. This is actually a map which is showing map of India, showing basic wind speed, right? Therefore, this let me show it in a iBird's view, student, right? This is how I'm just showing in a iBird's view, right? That is how the entire India, right? I'm there at this location, Hyderabad, right, where the basic wind speed is 44, right? That value I have taken, right? That input I have given, right? Now I hope you understand how I have given that input from this figure 1, page number 6, and K1 just now shown from table 1 of page number 7 for the general building 1, and K2. However, K2 need to be it depends upon the height, right? For 10, 15, 20 meters, it depends upon the height. I will go to the table 2 of page number 8. Let me go to that table 2 of page number 8, student, at a quicker pace. Just bear for a moment, right? Page number 8. I'm going to that page, right? This is the table, right? This table. Let me increase the font, right? Therefore, from this table, I am taking that. Table 2, right? I have assumed a terrain category of 1. Therefore, for 10 meter, this K2 factor is equal to 1.05, 15, 1.09, 21.12. I am bringing those coefficients as an input here, right? 1.05, 1.09, 1.12. For 30 meter, 1.5. However, my height of the building is just 14 meter. Therefore, only these two inputs are required, 1.05 and 1.9. Even these are not required actually, right? Therefore, once I get that, then next coefficient is K3. However, what is K3? K3 is a slope factor. However, the code says that from this class 6.3.3, some page number 8, the same page number 8. I don't have any value, because code says that the value shall be taken as 1. You please see this, right? K3, right, is given in the figure 1. However, in the absence of data, that value shall be taken, right? If the slope is not more than 3 degrees, then the K3 value may be taken as 1, right? Therefore, I'm taking that result as 1. However, this Hyderabad is not there in cyclone zone, therefore it is assumed as 1. Therefore, all these 4 inputs I am giving. Therefore, K4 is also 1. All these are 1, 1, K1 1, K3 1, K4 1. But K2 depends upon the height. Therefore, that is a 1.05 or 1.9. Now I'll get what is that speed at a height of Z. Therefore, that is that basic wind speed that multiplied by K1, K2, K3, K4. Therefore, now I'll get 46.2 at a height of 10 meters, whereas at a height of 15 meters, it now works out 47.96. Hence, what is that design wind speed, or PZ at that height? What is that wind pressure? PZ is equal to 0.6 VZ square. Therefore, that 0.6 multiplied by 46.2 whole square. That is actually in terms of Newton per square meters. Now I'll divide with 10 to the power 3. Now I'll get 1.281 kilonewton per meter square and 1.38 kilonewton per meter square. 1.38 kilonewton per meter square. These are the wind loads, student. I hope you understood how we are calculating the wind loads. And let us move quickly to the of the next one. Next one is the turf. These are the wind loads just now I concluded, student, right? I'll just increase the font, right? just now concluded. Now I'll move to the top, the earthquake calculation, student, right? This is how my earthquake, this is what just now concluded. I got 1.28 and 1.38 PZ at a height of 10 meters and 15 meters respectively, right? Then I'll move to earthquake calculations as per IS 1893 part 1 2016, right? This Hyderabad is located in zone 2. Therefore this is a figure 1. Let me go to that page number 11 of IS 1893 new code. This is a new code, student, right? Page number 11. Now this is a this is a map of India showing seismic zones of India. However, Hyderabad is located in this safe zone. Actually, it's a J zone 2, student, right? Which is the safest zone, right? Therefore, and for that zone, what is the zone factor? I have to have the zone factor as 0.1. I have to have the zone factor as 0.1 from this table. Now let me go to that formula also, right? I'll be using this linear static method for the analysis. Therefore, equivalent static method. Therefore, what is the design acceleration spectrum, right? The design seismic coefficient, horizontal seismic coefficient AH is given by this ZI by 2R SA by G, right? Rearranging fashion, Z by 2 SA by G, R by I. R is equal to ZI by 2R SA by G, where Z is the seismic zone factor given in the table 3 and I is the importance factor, right? Because my building is a normal building, therefore I'll take this importance factor as 1, and R is a response reduction factor, right? We'll see that. And SA by G is the design acceleration coefficient for different soil types, whereas the soil types are soil type 1 is a rock and soil type 2 is a medium or stiff soils, and soil type is soft rocks. However, the SBC of the site is 200 kilonewton per meter square. Therefore, I'm assuming soil type as medium. Therefore, if that is true, I am there in the equivalent static method, because it's a normal building where the height is also just 14 meters, which is less than 20 meters. Therefore, I can use this equivalent static method. Therefore, what is SA by G? It will be calculated. Before that, what is the time period? Natural time period. It will be calculated, right? For this medium soil, right? Therefore, based upon that, the SA by G value will be fixed. Either by the Excel sheet or that of the STAAD. Either of the two is true, right? Therefore, that is how these inputs are now given. Therefore, the zone factor is 0.1 from this table 3. Now I'll go to the page number 10, student. Now I'll go to page number 10, right? That is how the page number 10 of this 1893, right? This is my page number 10, where I do have the zone factor for this second zone as 0.1. You can observe, right? This is 0.1, right? And similarly, the other inputs that are required are like this. That the importance factor just now already told from class 6.4.2 page number 9, or even it is given in another table also, right? The same value is given, right? Now, response reduction factor, however, I am assuming it has ordinary movement resisting frame, student. Therefore, from this table 9 page number 20, let me go to that page number 20, student, right? Page number 20, right? Therefore, that is how my page number 20, the ordinary movement resisting frame. For that, the value is just 3. That is how we can see. Just now I told that even the importance factor is also given in table 8, student. For all other for important buildings it is 1.5. For other residential or commercial buildings where the more than 200 people are there, then 1.2. Even just now I have shown the calculation that I don't have even 32 flats multiplied by 4 means 128 people, which is less than 200. Therefore, importance factor is just only 1, right? Else, from this table 9, the movement frame system, I do have RC building with ordinary movement resisting frame, OMRF, right? Response reduction factor is equal to 3. Therefore, that input I'll give. In this Excel sheet or that of the STAAD also, right? However, the soil factor is 2 because it's a medium soil, just now I'll explain, and type of the structure is concrete structure. And from this page number 19, what is the damping ratio? I'll go to the right for concrete. In the absence of data, code says that the damping should be considered as this one, right? The value of the damping shall be taken as 5% from page number 19. From page number 19. Therefore, that input also I am giving to the code. Therefore, all these inputs I am giving to that of the code, right? Therefore, now I'll move to that of the STAAD. I think once you understood these inputs, student, right? I'll move to that of the STAAD, right? Therefore, let me just reduce the font size so that I can revisit it. Therefore, this is how my STAAD, right? So far I have explained the 3 designs, right? One, the design of the slab. Even I have shown the reinforcement detail. The second one, the design of the staircase. Even I have shown the reinforcement details and AutoCAD drawings also, executable, AutoCAD, good for construction, AutoCAD drawings. Third one, that of the plinth beam designs, even reinforcement details. Now we'll design that of the beams and that of the columns, right? Like this, that of this bare frame, right? Now what I have modeled in STAAD is only that of this bare frame, student, where now you can see at the bottom I have modeled that of the plinth beams, right? This is how that plinth beam, right? Or this is the ground floor, or this is the ground floor roof, this is the first floor roof, that of the second floor roof and terrace floor roof, right? There is how I do have ground floor, first floor, second floor, terrace floor roof, right? There is a G+3, and this is the roof of that staircase headroom. Now you can see in plan also, right? The eye bird's view, right? This is a one flat, right? There's a kitchen room, right? Attached toilet, right? Children bedroom, master bedroom, and hall, right? Like that. You can see the same is repeated, right? In 1, 2, 3, 4, 5, 6, and 7, 8 units, right? That is the STAAD model. Now I'll define. I'm there in the first page, setup page. I'm defining what is the job information. This is a 2 BHK apartment, right? And the client is structural engineering lectures, and who is the design engineer who has designed, what is the job number, etc. You can define who has designed, who has checked, who has approved. You can give that information. I'm just skipping off. Now I'm defining the geometry, right? I'm now having a model, a 3D model which is already generated. I'm not generating now, because generation of this requires some time. Therefore I'm just I hope that you can generate on your own. This is how the node, the first node is taken at the 0, 0, 0, 0, 0, 0, like that. The other nodes, right, are generated, right? The second node is generated at 3.0700, third node, so on and so forth, right? All these nodes are generated, and next I'll have these elements. This is how the first element connected between the node number 1 and node number 41. Node number 1 and node number 41. That is how this element connectivity table will establish the relation between the local degrees of freedom and global degrees of freedom, right? For further reading, you may just revisit our find element methods playlist for understanding what is the node, how the node numbering should be given, how the nodes should be created for a find element model, and how the element number should be, member number should be given, what is the element connectivity table between these two, and how the loads shall be assigned, where the nodes should be assigned, where the loads should be assigned. From that find element playlist, find element methods playlist, student, right? For further reading, I'll just skip off that. You can revisit it, right? Now once I do that, I don't let me go to that of the geometry page, right? I have just defined this. I don't require any other specification. Now sorry, I don't have any such definitions that of the other parameters, right? Therefore now I'll go to that of the general page. Within that I am there in the property toolbar, right? And now I'm defining that of these columns which are there at the periphery as 0.23 by 0.38. Now you can see, right? That is how all these are with 0.23 by 38. Even you can see the orientation, right? That of these, right? All these are oriented in the major span direction. Actually, this is my major span. Therefore, all these are oriented in major span direction, student, right? That is how the visualization can be easily done for each and every component using this STAAD or that of this any software or ETAB, etc. Right? Therefore, these are my sizes. The size of this column is 0.23 by 0.38, right? 9 inch by 1 feet 3 inch, 9 inch by 1 feet 3 inch, right? Likewise I have the that of the other columns, student, right? These are the other columns, that of the interior columns, right, whose size is equal to 9 inch by 1.5 feet, right? 9 inch by 1.5 feet, right? What is that? Now let us see, right? That is how, right? Even two exterior, rest that of the interiors, right? Even that of the interiors, right? Even their orientation also. This is 9 inch by 1.5 feet, or 230 mm by 450 mm. 230 mm by 450 mm, right? Now, once I have these columns, student, then what I'll do is, we already designed these plinth beams, right? That is how these plinth beams you already seen. Even we have designed using the Excel sheet. I'm not designing using this STAAD, student, right? Because they are already supported on the firm ground or that of the CRS masonry, right? Firm ground or that of the masonry. That is how the layout of the plinth beams using 0.23 width by the depth. The depth is 0.3. That is how the depth. Now you can see the depth of these beams is equal to 0.3 meter, 0.3, right? Once I examine this, now rest of these are that of the floor beams. All floor beams are 0.23 width by 0.4 is the depth. 0.4. This depth is 0.4. Why? Because the slab is 100 mm thick. Therefore, that 100 mm plus that of the beam web is 300 mm. Therefore, 300 mm plus 400 mm is the overall depth of these beams is 400 mm by 230 mm. 230 by 400 mm is the overall dimension. That is how you can see the 3D visualization of all these beams in the form of grid, perfect grid. The same plan I already shown in the starting, right? Or let me just revisit, right? That of this same grid, right? This is how this grid, I'm just showing this grid in AutoCAD. This grid I am showing in AutoCAD, right? That is what the beam layout, the same beam layout I am showing in iBird's view, or that of this 3D visualization. Now I told that during STAAD design I will show that of these mid-landing beams, right? These are the mid-landing beams of the staircase, and this is the staircase headroom. Two longitudinal beams and two cross beams, right? That is how all the beams are modeled using 0.23 by 0.4. Now then I don't have any beta angle specifications. Then now I will go to that of the other specifications, and now I'll define what are the movement releases, right? If I am saying that at the start of this secondary beam you release the movement along x as well as z direction, only along the major direction only it will be bending, but at the end, right, it will not carry any bending moment from the top of the main beam. Therefore, that is how I am just releasing at the start as well as at the end of the same beam. So now you can see, right, that blue color is changing from that start to end, right? Once I define these, then I'll go to the top of the support conditions, right? And now I'm having all the supports, the rigid supports fixed at the base, right? Like this, right? Fixed at the base, right? This elevation we already seen. This is what just front elevation, that of the bare frame, student. This elevation already shown here, right? Like this one, right? This elevation, right? Or that of the skeleton, right? Even if I remove these, right? This is what exactly in STAAD I am showing. This, right? This elevation I am showing, or this section I am showing in STAAD. That is the beauty of, or there is advantage of these softwares, right, in understanding the different geometries as well as that of the orientations of the beams and columns. Then once I do that, now I'll go to that of the next page as the loading page, student. Therefore, let me see the 3D view. Therefore, now I'll define, to start with, I'm defining these wind definitions, right? Just now we have calculated in the previous subheading that in the wind load and earthquake load, this 1.28 at 10 meter and at 15 meter 1.38. I'm just bringing and pasting here, right? Therefore, at 10 meter 1.28 and 1.38 at 15 meter height. At 15 meter height, 1.8 kilometer per meter square. But however, let us see what is my height, right? This is the bottom node, which is at y is equal to 0, and the topmost node is at 14 meters. Therefore, up to 15 meters, I am saying that 1.38 kilonewton per meter square. Therefore, that is my variation of the wind from 10 meter. At 10 meter, it is 1.28 kilonewton per meter square, varying from 10 to 15 meter from 1.28 to 1.38 kilonewton per meter square. 1.38 kilonewton per meter square. Right? That is all the wind definitions in the load page. Right? Similarly, now I'll define that of the seismic definitions. Though I am showing 1893-2002 code, student, right? The same is also applicable as per the 2016 code also, because I am there in the linear static method. Therefore, that is how my definitions, right? Already explained, right? Zone factor is equal to 0.2, right? Response direction factor 3, and importance factor is equal to 2. The rock or soil factor is equal to 2. The type of the structure is RCC structure 1. The damping value is equal to 0.05, and the depth of the foundation is assumed at 2 meters. Right? Therefore, these are my definitions. Then I'll add automatically the self-weight, right, and that of the member weights, right, for considering the lumped mass, right. For considering the lumped mass, I'm considering all these loads acting on these beams, right, at different levels, right. Even at parapet level, 1.95. That of these intermediate walls at the rate of 4.25, and that of the exterior 150 mm thick, 6.5 kilonewton per meter, right. And that of these 5.75, right. All member weights. Similarly, I'll consider all the floor weights, that of the dead loads, right, acting at different floor levels, as well as now I'll consider that of the live loads also. However, you please see that the live loads are reduced as per the IS 1893. They are reduced by because the live load intensity is not more than 3. Therefore, only 25% can be considered. 25% can be considered. Therefore, 2 multiplied by 25% now works out 0.5 kilonewton per meter square. 0.5. Even that of the 1.5 divided by 4, 0.375. Even the others also, that is just reduced, right, or 1 kilonewton per meter square. In the extra live load divided by 4, that works out 0.25 kilonewton per meter square. That is how all these floor weights are considered as lumped masses, right. Now once I do that, what now I'll do is I'll go to that of the I'll close this page, student. Now I'll go to the definitions, right. That is how actually already analyzed. You can see that the seismic weight is acting in x direction. Therefore, that is how all the lumped masses are acting, right, now in x direction, positive x direction. Similarly, all the lumped masses are acting in the positive z direction. You can see the lumped masses are lumped here, right? Because already done the analysis, right? Now once I see that, now I will go to the top of the all these red means the sulfate, right? Then let me go to the top of these loads, right? Therefore, this is our 3.75 kilometer per meter square at all the floors, right? Starting from the ground floor slab to the top of the terrace floor slab. Ground, first, second, and terrace floor slabs all are having 3.75. Now this 1.5 is assumed extra. Now let me show that at a quicker pace, student. I'll show that, right? And I'll come to that. Now let me just wait for a moment. I'll show that. I'll go to, I'm there in the STAAD editor. Therefore, I'm just defining these dead loads. I'm defining these dead loads. Yes. Therefore, just now we have seen this 3.75. Whereas from Y range 5 meter to 11 meter, this floor load is 1.5. At X range from 0 to 1.975 meter, in the Z range 0 to 2.785 meter. That is how I'm just defining all this. Wherever the additional loads are there that I am defining. Or let me take one floor and I'll show. Let me just pick up one floor, student, then you will understand what I'm just picking up that of a ground floor roof. I'm showing it's a 3D view, right? 3D loading. Therefore, just now I clicked this sulfate. Yes, I'm having this, right? And now even you can see that I do have this 3.75. But now you can see that, right? Just this 1.5 is acting here. What is that? Is if I go to the actual planning, right? Here I do have toilet. Therefore, I'll even wash area. Therefore, I'll assume that I am just having an additional load of 1.5 kilonewton per meter square. 1.5 kilonewton per meter square for filling of the cinder. Or because I'll be having an height. of at least 100 mm to 150 mm for toilets, for putting the nanny traps. Therefore, there the filling by the cinder, or even in the wash area also. Therefore, that filling weight is considered as 1.5 kilonewton per meter square. Like that, even now I'll have even here in this zone, right? Like that, wherever such toilets or that of the washroom areas are there we are defining this 1.5 kilonewton per meter square. Now you can see, right, it is changing, right, location to location, right? Now I'm there here, right, here 1.5 kilonewton per meter square, right? 1.5 kilonewton per meter square. Even now here 1.5, so on and so forth, right? Once I examine the student, now I'll go to the top of the this what is 17.6 as the load reaction from the top of the staircase, right? Therefore, there is now taken care. And also these are the loads from 150 mm thick on the periphery walls, because this is my one flat. Therefore, this is my peripheral wall of 150 mm, right? And this is the second flat. Therefore, peripheral wall with 6.5 kilonewton per meter. 6.5 kilonewton per meter. Similarly, now I have 100 mm thick walls, right, which are loaded with 4.25 kilonewton per meter. That just now shown in the plan also, right? You can see that here I do have a wall, right? Therefore, this wall weight is considered as 4.25, whereas this non-model is already taken care in the case of the floor finishes, as well as now also we have taken the cinder load. Therefore, it will be captured, right? However, this wall is modeled in STAAD. However, just now we have seen that this beam is having a movement release here as well as a movement release here, because this is a simply supported beam, right? That is how the STAAD. In the STAAD, I do have the loads of 4.25 kilonewton per meter, and that of the other loads at the other levels, right? Now once I see that, now similarly let us see the live loads. Therefore on each floor I have to have a live load of 2 kilonewton per meter square, and 2 kilonewton per meter square. Even I have to have this additional 1.5 kilonewton per meter square at that of the terrace floor, student. Now sorry, this is the live load at the terrace floor. This is the live load at typical floor, ground floor, first floor roof, second floor roof, not terrace floor. At terrace floor roof, that is 1.5 kilonewton per meter square, whereas this 1 kilonewton per meter square, because the corridors will be loaded with 3 kilonewton per meter square. Just now we have just loaded with the 2 kilonewton per meter square. Therefore additionally I need to load with 1 kilonewton per meter square. Just that I am loading. However, just now we have seen that the reaction in the loads, actually let me go to that loads, student, right? This is how in the loads, right? This is how 6.5, 1.5, this is how 11.5, 17.5 and 11.5, 17.5 and 11.5. Therefore this is how 17.5, the load on the staircase, from the staircase, as well as this 11.5 load from the staircase onto the beam, or that of the mid landing beam as appropriate. Therefore all the dead loads and live loads are shown. Now we'll go to that of the wind loads. If wind is acting, you please see, for understanding it is so easy actually, right? The panel width is half of that height of the height of this floor to half of that height of this floor, right? Therefore if I see that of this side view, student, now there is a this exposed area, right? Therefore this beam is getting a load from this piece and this piece, right? Whereas this beam is getting a load from this triangular area of this exposed area, right? And this beam is getting from this trapezoidal loading, right? That is how these beams are getting from this rectangular loading, right? So on and so forth, right? It is so easy for understanding actually, right? Now I hope you understood how the loads are coming onto the beams also. Even if you are further interested how the loads will be coming onto the beams using manual calculations, the other day we already examined in the previous video. Just revisit that video, student, previous video, right? That is how the loads will come onto each of these beams, right? That of the dead load or live loads, etc., right? That is how these loads will be acting at the nodes. Wherever there is a node, there only the load will be acting in FEM, in finite element methods, right? Therefore, for how these loads will be acting, if you are further interested, you just go to visit our finite element methods playlist, student. Then you will understand. Therefore, these are the loads from positive x direction. Similarly, that of the wind loads from other directions. Right now, you can see if the wind is blowing from the positive z direction, right? That is how the wind is blowing from the positive z direction, student, right? And the right, you please see, right, the positive z direction, right? When wind is blowing from the positive direction, right? These are the loads acting at the different locations, or nodes, different nodes, right? If the wind is blowing from the negative x direction, wind is right, wind has changed its direction, right? Positive to negative, right? Similarly, if wind is blowing from the negative z direction, right? These are the loads that are acting at different locations, right? STAAD will follow this format, student, right? X, Y, Z, right? It is X, Y, Z, right? Positive X, negative X, right? Positive Z, negative Z, right? Positive Z, negative Z, right? These are what the notations, right? Once I see, then what I'll do is now I'll move to the top all the dead load and live load combinations, right? Now let me also say, before I go to the dead load and live load, let me take the holistic view, right? That is how, now let me see, right? That is how the wind loads are acting on the entire structure, right? That is how the entire on the entire structure, the wind is acting like this. The wind is acting like this, right? From positive x direction, as well as that of the positive z direction, student, right? Positive z direction, as well as that of the negative x direction, right? And as well as that of the positive z direction. Even you can see the exposed area from which these beams are getting the loads, these beams are getting the loads. Or if I see the front view, then you can see, yes, each of these loads are transferred onto each of these beams, right? That is the advantage of using these softwares, STAAD or ETAP, so that you can visualize what is happening to the load transfer mechanism, how the load is transferred from the one member to that of the other member, from beams to that of the columns to that of the footings, right? There's advantage of these software, student, right? Once I see this, now what I'll do is I'm just defining this concrete as my material. That Young's modulus is equal to 5000 multiplied by M25 grade concrete, therefore 5000 square root of FCK 5, therefore 25,000 or 25 kilonewton per mm square, and Poisson's ratio is equal to by default 0.17, and my FCK is equal to 25 kilonewton per meter square. These are my different input values. I have defined the material also. Now what I'll do is I'll close this general page. Now I'll go to analysis page. Then I'll analyze just normal, right? Perform analysis only. No printout, right? Then I'll go to the top of the design page, right? Now I'm there in the design page, student. Now I'm there in the concrete page, IS 456 page, right? There I'll go to the top of this concrete toolbar. There I'm just initiating the concrete design. I'm using Indian code. All these columns are assumed with 40 mm clear cover, and all these beams, either plinth beams or that of the roof beams, are assumed with 25 grade concrete, and the main shield 500, and that of the secondary shield is also 500 grade shield, right? Maximum main diameter of the bar is equal to 16 mm in all the members, and maximum secondary steel 10 mm. Minimum main steel is 12 mm. Minimum secondary steel as 8 mm. The reinforcement is 0. Reinforcement 0 means we are assuming tied columns, right? Ties, right? Ratio is equal to 4, means maximum percentage of reinforcement I am saying 4. As per the code, it should not be more than 6%. Now we are saying range means distance at the start and end of the point member from the nearest support, so as to consider the effects, right? Now, and also ensh means perform shear check against enhanced shear at a distance of 0.1, means yes, you consider, right? Now I'm asking, I'm doing these column designs what I have highlighted, as well as these columns, right? All the columns I'm showing, right? All these columns, as well as I'm also designing all these beams, right? There's all these plinth beams, as well as that of the floor beams, right? Therefore, once I'll do this, now I'll say end concrete design. Then once I click run analysis, then I'm getting the output just within. Now let me see these outputs, right? Therefore, I just concluded that and right, what I'm getting, I'm getting a few warnings, and I'm getting so many warnings, but right, nevertheless, now I'm going to the top the output now. Therefore, now all the results are displayed just in 21 seconds. The analysis is performed, right? Sorry, before I go for the analysis, student, let me just show the load combinations. Right? Therefore, so far we already defined these loads, primary loads, right? Dead load as this combination 3, and live load as combination live load as 4. Therefore, now we'll take the load combinations for designs of these footings, right? Load combination 9, dead load plus live load 1 plus 1, 3 multiplied by 1, 3 multiplied by 1, and 4 multiplied by 1, 4 multiplied by 1, 4 multiplied by 1. Therefore, similarly, the dead load plus earthquake 3 is the dead load, whereas earthquake in positive acceleration is 1. That 1 multiplied by partial safety factor for this one is 1, right? Similarly, the load combination 11 from negative x direction, therefore 3, 1, minus 1. Please see this factor as minus 1. Similarly, earthquake from Z direction, 3 dead load multiplied by 1, 2 multiplied by 1. Similarly, from minus Z direction, 3 multiplied by 1, 2 multiplied by minus 1. Similarly, that of the wind from X direction, 3 multiplied by 1, 5 multiplied by 1. From negative X direction of wind, 3, 6, 1, 1. And 3, 7, 1, 1, 3, 8, 1, 1. Now I'll move to the top, the dead load, live load and earthquake combination. Therefore, in such a case, as per the code, for the live load and earthquake load, I can reduce by 20%. Therefore, 3 multiplied by 100%, 4 live load multiplied by 0.8 and earthquake from X direction or X positive X or negative X direction, 0.8, 0.8 or minus 0.8 as appropriate. Similarly, for wind also you can see same, right? Therefore, I have just concluded all these load combinations from combination number 9 to that of the combination number 25, right? Now once I do that, what now I'll do is I'll go to the top of the limit state of strength combinations. Previously we have seen limit state of serviceability. Therefore, now this is a load combination 26, 1.5 multiplied by dead load, right? 3 multiplied by 1.5, like that. 1.5 multiplied by dead load plus earthquake load, 3 multiplied by 1.5, 1 multiplied by 1.5, 1 multiplied by 1.5, and similarly minus 1.5, 2 multiplied by 1.5 minus 1.5, right? 1.5, and similarly that of the wind loads also, wind loads, right? Therefore, that of the 6, 7, 8, so on and so forth. Whereas dead load, live load, wind load combinations, 3 multiplied by 1.2, 4 multiplied by 1.2, 5 multiplied by 1.2, right? All such combinations, right? Therefore, with wind 1, 2, right? 5, 6, 7, 8, right? All these are considered. Even with earthquake, I am considering 1, minus 1, 2, minus 2, right? Now, that of the stability point of view, 0.9 dead load multiplied by 1.5 earthquake load. Therefore, 1 minus 1, 2 with 1.5, 2 minus 1.5, right? Or wind load, wind positive X, negative X, positive Z, negative Z. Therefore, I have just defined from load combination 30. Sorry, this load combination 26 to 50. 26 load combinations I have defined, student, right? Therefore, that is how I have defined 26 load combinations for limit state of serviceability, as well as 26 combinations for that of the footing designs also. Now let us go to the top the designs of the columns and that of the beams, right? Now I think I hope you understood the discussions what we had in today's class, student. And in today's class we have seen the analysis and design of a ground plus 3 floor RCC framed building. We'll meet in the next class with another discussion of there we have designed the slab, beam, column, footing and staircase also using Excel sheets. I think now we'll conclude the session. If you like what we had in today's class, all the discussion, don't forget to click like, comment, subscribe and share to our YouTube channel, right? Till then, bye bye students.